All right, we are going to work on replacing uh, to a vector with a moment about a different point. So it's relatively simple. We're going to do a moment about O is equal to R, and I'm going to use the dot, times the force. Okay, it could be equal to R, and it could be A over B directions times the force. You could see it a lot of ways here, but important note, must do the distance first. And I'll explain that a little bit. Must do distance first in the equation, as it's going to help with equation, not equal. Okay, it'll help to determine the sign of where this thing's going. And long run, if you messed it up, you got a negative number. It's not going to change the world too much, but to be accurate, you want to pay attention here. Okay, so let's do this. We got a origin here, and let's not do that there. Let's do this, and we'll go up here, and that'll be y. And I'm going to bring the x out in that direction. Let's see if I can not drag my hand across the surface. X in that direction. Okay, and then out here we will do a vector like so, and we're going to have some angle theta, and this is going to be known as point A, and this one back here is the origin. So ideally I got z going in that direction. So y, x, and z we've identified. This distance from here to there is known as the radius of the moment. Okay, and that's perfectly understandable. We call it a radius. Could just be a d for distance, but it's still the same thing. Okay, and what we're looking at is this. R is going to be equal to x times I plus y times j plus z times k. And then our force will be equal to f of x I plus f of y j plus f of z k. Okay, and that will apply all the things we need to making this solution. But what we're really looking for is this. We want to see what this moment would be here. So this is our moment about O. So force F is going to cause some rotation about the origin, or point O in this place. Okay. Let's see, what else do I want to tell you about this before we go on? Oh yeah, the other thing is, should have done this. There's an assumption up here to just this problem, not to every assumption in this problem is F is in the XZ plane. Okay, so it's not vertical, it's back at an angle. Alright, I guess the other bit we could do with this is, let's do that. We got this and this, so it helps lay that out there. So basically the vector F is laying flat on the XY plane, or XZ plane, okay, cool. One other side note here, so I'm going to just put it down as a side note, just so that you get used to this. Later you're going to see things that the moment is equal to force times distance, and we spent a lot of time with that in strength of materials, but you might as well know what it is now, and that's really no different than this distance and that force. So F, and we're measuring that D across there, okay, and it's moving about that point. So a moment here would be something in that direction, and that'd be our moment. Okay, that's what that's all about. Now, the easiest way to do this one, I think, is to explain this to you with a full example. So we're going to work this out and see how far I can get through this before we get caught into the trying to keep the time limit short on these things. All right, so let's do this. I'm going to set this up. We're going to do a wall here, and then I'm going to do a see if I get this somewhat in perspective here. Okay, and we're going to put a point right there, and I'm going out in that direction. Actually, that's not even close. It's more like that direction. Okay, and this, and I'm going to have an angle of theta in here that's 70 degrees. That's a degree symbol. And I'm going to have from the center line down through here, we're going to have 400 millimeters to the wall, to the center line, to actually where point A is. Back here on the wall, this will be point B. And then we're going to come up to here and make it 260 millimeters. Okay, so that's our structure. And just so that we have some plane of reference here, this is a positive X, and that is a positive Y. Okay. All right. Now, I'm going to lay this in here, and we'll come back and refer to it again and again. And then we're also going to see our favorite friends, the vector identities, come around. If a moment goes in this direction, where this is I, J, and K, this will be positive, but if the moment goes in the other direction, that one will be negative. So positive, negative direction of the moment. Okay? All right. So, how to set this problem up. And we're going to start teaching you a little bit more about engineering format of your solution. So we're going to write out a title of this. So we're looking at the moment arm, and I'm going to label it R A/B, and I'm going to underline that, and then I'm going to write it just as you would seen it in previous problems. R A/B is equal to negative 0.4 meters. So the 400 millimeters is 0.4 millimeters, or 4.4 meters. It's negative because it's going from B over to A, so it's a negative sign. And we're going to put an I in there so we know which plane it's acting on. Plus, we're going positive in the Y direction, so 0.26 meters, and that's a J. And that is the solution to the moment arm. Okay, fairly simple. Now we need the force vector components. Okay, and I'm going to label that as F. Okay, and I guess I want to point out one other thing, so let me do this in red if I'm going to do a little different note here. So think about A right here. Okay, we're going to have a vector here of Fy and a component of Fx there. And our B is way over here. And when we get done with B, we're going to have a moment that's doing something like this. Or that way. We don't really know exactly until we get a solution, okay? But that'll be our moment about B. Okay, that's point A. Now, each of those is going to drag this thing around one way or the other. So it's kind of what we're looking at. And I guess as long as I'm having fun here, let's do this. Draw the object in there so you can see it. All right. But those components Fy and Fx are going to cause some rotation about point B. That's what a moment's really all about. Okay. Off the side note, back to making a solution here. All right, so I'm looking for the force on this. So we're going to write this as F is equal to the, oh, I didn't give this to you in the problem up here, did I? 600 newtons is the force. Okay, and I guess let's do this. If I'm going to do it right, we're going to do force cosine theta, and that'll be in the I, plus force sine of theta, and that'll be in the J. And really it's just coming out of all the basic trigonometry we did earlier so far in this course. So if you're stuck there, go back and take a look or send me a message and let me know you're confused and still having problems. But now I'm going to substitute numbers in. So my proper engineering format is to write out the equation without numbers in it, and then do the numbers in place, and then write the solution. So a three-step process to all math equations in statics. Oops, I forgot to put the 70 degrees in here. And that's J. And that's that. Now, if I solve for this, I'm going to get 205 newtons. And that's still in my I, so I want to keep track of those I's and J's as we go through this. And I'm 564 newtons. And that's in the J. Now, the other thing is, note, always write your units out. Okay. Without the units, you have no idea what you're solving for, and most of the mistakes are made because the units don't agree with what we're actually trying to solve for. Okay. All right. So we now have our magnitude and direction for our vector. We have our arm for the moment arm, and we can actually go find the moment now. So I'm in black. I'm going to write this out. Moment about B, and it's going to be M sub B, and underline it. And you can start seeing how I lay out the paper or the calculations down a sheet of comp paper. All right, so write M sub B equals to the radius of R slash B. So we have two numbers there, that's why we write that way, times the F of what we're looking for. And I'm going to put things in. Okay. Now, minus 0.4, okay, from up there, meters, and that's I, plus 0.26 meters, and that's J, okay, and then we're going to multiply it times 205 newtons in the I plus 564 newtons in the J. Okay. Now the next step, it gets a little complicated. I'm going to do it out all the way so you can actually see what's happening here, but I want you to get the hang of this. But this next step isn't required, so actually maybe what I'll do is put that in red. I'm going to multiply this out, and I'm going to take negative 0.4 meters times I times 205 newtons times I. Okay. Then I'm going to go over, so negative 0.4 meters times, oh, and this is, don't forget the I. Nope, that's a J. I times 564 newtons times J. Lump that together. And we're going to do plus 0.26 meters times J. That goes over and multiplies times 205 newtons times I. And then the last one is plus 0.26 meters J times 564 newtons times J. All right, now here's where the math gets in here. And you can remember this down the road. You don't have to do all this step if you just remember this. So if you go back to your vector identities, I times I was 0. So 0. I times J comes out as a K. Okay. J times I is a negative K. J times J is 0. So what we're getting in the solution is this. We're going to get negative 225.6 Newton meters, because we're multiplying meters and the Newton, so it's Newton meters. Write it out this way. All right, I'm going to put this on here, and I get a K value. Okay, plus 53.3 Newton meters negative K. All right, and you could skip this step and go right to this one. Depends on how gutsy you are. If you make a mistake, I can see where you made the mistake if I can see all the work. But as long as you get there in the end, that's the important part. Okay, and that's K. So everything turns out to be a moment about K. Well, remember what that moment is. That's going to be about this axis, like this, and that's K. Okay, and K is on the Z plane. Okay, and we'll deal with that here in a minute. I'm going to go back to the other drawing, but my final answer is negative 279 Newton meters K. Okay. Make sure you're seeing what I'm seeing. We're good. Now, if I go back up to this problem, and I was trying to figure out which way this moment goes here, then I'm going to take it about point B, and I add negative 279. So the moment about B was negative 279. Okay, and using the right-hand rule, we will put our thumb in the direction of that moment. So if I'm negative, I am going to the right, which means my moment here is, let's get rid of this, my moment is going to be that way, okay? And this just becomes positive at that point, and that's Newton meters. But that tells me that my thumb is pointing into the surface. Did I do that math right? Something's really messing me up here. Explain that F is the largest unchecked moment, and F will pull our ambient slightly right hand force vector points to into the wall. No, sorry. This is I think I got myself screwed up here. Not sure where I did it though. Negative, negative, positive, positive, negative, negative, 279. So 279 is right. I'm just getting the direction of this moment wrong, and I'm not sure what I did wrong here. I should see the right-hand rule. I should place my thumb pointing in towards B or in through the page, and my finger sweeping to the right, which means this vector is, or this moment is actually in that direction. And that would be negative. There we go. And so that's positive up here though. So positive's going to the right, negative's going that way. I think I got it. I think I got it wrong on my notes. We're going here. We'll check this again when I do another problem for you. Okay. So that's the rotation that that moment's going to do. And F is going that way, pulling up. Now, it's got to go down. I know it's got to go down. It's got to go this way. And here's my logic. Okay, so if F is rotating up and to the right, I got to have the equal and opposite reaction due to that force. No, I had it right. Sorry. It's this way because it's negative. It goes this way. Okay. All right. So actually, right hand rule. I put my palm on the page, thumbs pointing upward, fingers are curling to the left, counterclockwise. That's the rule. That's how that works. All right. So here's how this works. Let's blow this up for a little bit. I want to spend some time doing this. But if f of x is at 0.26 meters here, it's going to try and rotate this whole thing and bend it something like this. Okay? And then f of y is going to try and stretch it out vertically, and it's going to pull it. So we're doing this kind of thing like this, and we're going to pull it up away from this point. We need to be able to counteract that as it's trying to do that. So cool. We'll see more examples. I got another one coming up, and that'll help sort that out. And that is about my 15 minutes or so. So I think we'll pause there, and I'll set up for another example, and we'll go from there.